Hello! Now that you have studied how to read phase diagrams for soluble materials, we're ready to jump into insoluble materials. We're going to start with a binary system or two materials. Let's make sure we understand what we mean by insoluble. Insoluble materials are those that, while they may be soluble as liquids, once they become solids, they cannot mix. Their atoms are of different sizes, they can't be held interstitially or interchangeably, and they have to actually cool as separate solids that could then layer. We saw something similar to this when we looked at adding ice and salt together, and of course when we dumped the ice out, we saw that we still had all of our salt as a solid. Now in reality, you're not mixing just as solids, but they don't mix as solids in soluble materials, but you're not necessarily mixing them in their solid state. Even if you mix them in a liquid phase where they can be soluble, when they start cooling and solidifying, they actually separate back out and become two separate solids. And so they're going to create microscopic layerings of those individual materials. Now remember, we saw something similar to this when we were just introducing solubility in Module 5, and we saw that once we get above 0.022%, iron can't hold carbon anymore, so it's only partially soluble. Above that percentage, it behaves like an insoluble material, and we saw that instead of having any sort of trading of atoms, we would get back out these separate layers of pure iron and iron carbide. And those were the black and white lines in our grain structure. So let's see how we can use phase diagrams to start to understand this behavior when we are insoluble. So here's what our phase diagram looks like. It's a little bit different. Before we even jump into our liquidus and our solidus and what that might look like, I want to bring your attention to the bottom where we're talking about the composition by weight. Some phase diagrams, whether they're soluble, insoluble, or partially soluble, will instead of putting composition by weight at the top and bottom, they might put both at the bottom. So here we have, moving from left to right, our percentage of material B, and so just below that is then our percentage of material A. And obviously if I'm, say, at 40% A, I'm at the equivalent of 60% B. So as we look at this phase diagram, and I want to point out to you that you can download the slides if you want, and you could be drawing right along on a blank copy of this on the slides, but you're going to get a chance to do an activity here in just a moment. So if you want to just follow along now and then do your activity and draw on that, that's fine as well. So here as we look at this phase diagram, we're going to see that our liquidus is a little bit different shaped. So here is our liquidus. It still starts at the melting point of A and does continue to the melting point of B, but instead of being a continuous arc, we end up with two liquidus curves that come together and meet at some point. They meet there at that horizontal line. Now that horizontal line is actually our solidus. Now our solidus also goes from the melting point at A to the melting point at B, just like it did for soluble materials, but this time it's a vertical line when I'm 100% A and a vertical line when I'm 100% B, and then it's a horizontal line that's at the level where the two liquidus lines come together. Now just like in our soluble materials, if we are above the liquidus, our material is 100% liquid. If we are below the solidus, we are 100% solid, but now instead of being a new material that has intermixed atoms from our materials A and B, instead we are a new material, but it's more like a composite. It's made up of small microscopic parts of A and B. So in our solid, we're going to say we have both solid A and solid B, and we're adding them together. Now another thing that's a little bit different here, and this is really important, when we drop below the liquidus, only one material can start solidifying. Just one. The other must remain liquid until we drop below the solidus. To know which material is going to start solidifying, it really just depends on your percent composition of your original material. If your percent composition of your original material ends up, if you draw just the vertical line that says, hey, I'm starting with X% of A and X% of B, if that vertical line you draw is to the left of that point where the liquidus comes together, then only material A can solidify below the liquidus until you get to the solidus. If your percent composition, when you draw the original line, vertical line just indicating your percent composition, if that is to the right of that point where our two liquidus curves come together, then only material B is solidifying below the liquidus until you hit the solidus. And of course, if B is solidifying, then there's going to be less and less B in your liquid as you're cooling. So let's actually look at an example of what that might look like. So we're going to start with a material that's 80% A and 20% B. So when we draw our vertical line representing it, we can definitely see that we are to the left of that point where our two liquidus curves come together. So only material A is going to get to solidify. Notice, because I don't have the percent by weight of material A on the top of the curve, I don't need to extend my line any higher than the liquidus, my percent composition line. All right, now we want to know what's happening if we're at some temperature T1, so we can put T1 on our curve, and we'll draw our horizontal line just like we did for soluble materials. Where that crosses the liquidus, we can drop down a vertical line and start to see what is the percent composition in our liquid of material A and B when we're at temperature T1, and it looks like we're about 30% B and 70% A. And if we look to where our horizontal temperature line hits our solidus, it actually is hitting already at a vertical line, so we don't need to draw a new line. It's hitting at the vertical line that says we have 100% A in our solid and 0% B, which is what we said has to happen. So at T1, the solid is 100% material A, the liquid is 30% B, and 70% A. Now, because A is the only one solidifying, there's going to be less A now in the liquid, so its percent of the liquid goes down, and B's percent, which B is not changing mass in the liquid, so its percent has to go up a little bit. So let's continue dropping our temperature down to T2, and we can extend out our temperature line to hit the liquidus and the solidus. When we drop our liquidus line down, we're going to end up at about 50-50 A and B. And of course, if we extend, still our temperature line is extended to the solidus. And when we drop down from that vertical line, we're still sitting at 100% material A is solid, and none of the solid is material B. So again, 100% A, liquid is about 50-50 at temperature 2. Let's keep cooling, but this time let's go down basically to the solidus line. So let's put T3 right about at the solidus. So if I were to draw a horizontal line at my temperature, I'm basically drawing along the solidus. I can drop down that vertical line, and I'm going to see that my percent composition in my liquid is maybe 59% material B and 41% material A. And for the moment, basically our solid is still 100% material A. Now it's really interesting, we have been seeing that the percent of B in the liquid is continuing to rise. As A is solidifying, there's less A in the liquid, so B starts making a greater percentage. And that shouldn't be surprising, but that's important. Now, the moment we get below the solidus, as the temperature is cooling, now everything can solidify. But this composition, this 59% B and 41% A, that's right where those two liquidus points come together, and that's really important. So that point where those two liquidus lines come together, we're now going to label. That's what we call the eutectic point. The eutectic point solidifies the temperature and the percent composition where both materials can begin to solidify. That percent composition is also known as the eutectic composition. So on this example, it's 59% B and 41% A. Now, what the eutectic composition represents is if I have a mixture of material A and B, it is the percent composition in the liquid that is the lowest melting point. So we can actually lower the melting point of this composition, and at its lowest point, you'd have to have 59% B and 41% A. And we can see how much lower that melting point is than A or B's original point. And that's one of the reasons to mix together, is you can lower melting points, as opposed to sometimes you mix together because then the behavior of the resulting solid gets to use some of the behavior of the solid of A and some of the behavior of the solid of B, and you can get the best of both worlds. Now I want you to think of salt water, because salt water is insoluble, and when we add salt to our water and they start to solidify, we actually lower the freezing temperature of pure water. So once the salt's in there, we can actually keep the liquid as a liquid for longer so it doesn't freeze as soon. And of course, we then salt our roads, or people salt their driveways or sidewalks in cold areas because you don't want it to freeze as soon. And so there is a set percent composition of how much salt to add to your water to give you that lowest possible melting point, which would also be then the lowest possible freezing point. So what I want you to do now is you have a handout. In fact, pause here, complete the exercise, and then come back and check your solution. So let's look at what we had. First off, the first question asked, what's the name of that point where your two liquidus lines joins? And that is the very important eutectic point, which tells us the percent composition. That's our lowest melting point and where all the material can begin to solidify. So it also asked us in this problem to find what was happening for something that was originally 80% material B and 20% material A. So we can draw that line representing our original composition. We were told we were at temperature T, and we wanted at temperature T to determine the percent of A and B in the liquid portion. So we can draw our vertical line to represent, and I would estimate that it's at about 45% A in the liquid and 55% B in the liquid. That was my estimation. We were also asked to find how much of A is in the solid and how much of B. Well, if we look at our temperature line and where it hits the solidus, and here's our solidus line, that red line that is our solidus, we can see that if we drop a vertical line from where our temperature line hits the solidus, we're going to be at 100% material B in the solid and 0% material A. Now this activity also asks you to go ahead and determine the percent of liquid and solid at temperature T. So how much of B has solidified? So what's our mass? Now you weren't given a total mass, but instead instructed to go ahead and find it as a percent of the total mass. So let's see what our mass balance equations look like. So we can start with just material B, and we know we said we started with material B being 80% of the total mass. We established it's about 55% of the liquid, and it's going to be 100% of the solid. So that's our equation 1. Our equation 2 is just the total mass equals the mass of the liquid plus the mass of the solid. Since we don't know the total mass, we can go ahead and just rewrite this either in terms of the solid or the liquid. So I wrote it as the mass of the liquid is just the mass of the total minus the mass of the solid. And if we plug equation 2 back into equation 1, we're going to come up with this expression, which we now can see just has the mass of the solid in it and the mass total. So if we solve this for the mass of the solid, we get that it is 55% of the total mass. So the liquid is going to be just over 44%. We could have also done this with material A, and material A would have been easier because we have 20% of our total mass is material A, and we said that 45% of it is in the liquid, but we said 0% is in the solid. So when we put that 0% in, the mass of the solid term goes away, and we can immediately write the mass of the liquid in terms of the total mass and get back out that the mass of the liquid is that 44.4%. So our mass of our solid is 55.6%. So I hope this example helps you understand how to read a binary diagram with insoluble elements. You're going to have more opportunities to do this. Both for soluble and insoluble, you should be able to pull off numbers like this, and understanding both of these will help us understand the more challenging partially soluble phase diagrams, which is your next exercise.